Okay, so we can start with our first speaker of this morning session, Monica Wong, and she will talk about Reconstruct the Shock History in NGC 253 with ALCHEMI. Monica, the floor is yours.
Thanks. Thank you. First of all, thank you for all the organizers and thank you for having me here. So in this talk, I'm going to highlight some of our recent new results with ALCHEMI, which is the ALMA large program, and we imaged the nearby starburst galaxy NGC 253. And in particular, in this paper that we just submitted, we studied the shock. And in the end phase of the study, we actually realized we are able to reconstruct a shock history, which is pretty fun journey. So hopefully at the end of this talk, you will also enjoy like we all do. So sorry, to set the stage, ALCHEMI, like it's a large program. It's in one sentence, it's a spectral scanning from ALMA band 3 to band 7 with a homogeneous spatial resolution about 28 parsec, which is comparable to the giant molecular cloud size, GM size. And this size is actually a very nice fundamental unit when we want to study the gas properties and assume that is homogeneous property over there in like sampled by individual beam. So this scanning is pitched towards the nearby starburst galaxy NGC 253 with distance only less than 4 megaparsec, and this galaxy is almost edge on. So we are basically looking at the laying out there. So in this study, we utilized 11 HNCO transitions and 6 IO transitions. Both molecules has been long suspected to be good shock tracers, but potentially pointing to different types of shocks, which I will explain in a minute. So basically, this is the data we use, and here is the flow of thinking in our analysis. So we started having the observations, the green block. We are like building up our blocks here. So starting with the observational data, many transitions we have, and we have to use LTE to build up a good preliminary understanding of the gas properties, including the gas temperature, molecular gas column density, etc. But as you know, there's a lot out of this LTE thinking, so we must proceed to perform a non-LTE radiative transfer analysis, where we use RADAX and RADAX with spatial inference analysis to get a good estimate of the gas properties, including the gas temperature, gas density, etc. So in parallel to this massive block here, we perform the chemical modeling, which is on the right-hand side in the pink block here. So, by putting two parts of analysis, radiation modeling and also chemical modeling, we actually wanted to see if the analysis from the both sides, because they kind of provide different pieces of information, but in the end, we want to see if these two parts of information, whether they can be a consistent and coherent way. That is to say, do those analysis and results meet in the midst and give us a comprehensive picture of the shock in the field that we study here. So this is my one slide effort in summarizing what we have in terms of data products. So on the left-hand side, we have all the HNCO transitions sampled from individual GMC regions across the central molecular zone of this first galaxy. So an individual little mini plot here is the HNCO transition slab, like molecular ladder, basically. So for HNCO, so the trend for HNCO is highly varying from one region to another. For example, this orange, it kind of peak in somewhere in the middle before the black ones that I marked here is from the very beginning. So this somewhat already hinted that the excitation conditions for HNCO is highly varying across the CMZ. As a good contrast, SIO seems to have a trend across, the entire CMZ. So this gives us, this is actually a very strong that pushes us towards the non-LTE radiative transfer analysis. So, this on this page, I show some representative regions from our radix analysis. The pitch is actually somewhat different gas conditions, but they are all telling a coherent story. So in our Bayesian inference process, that this radix analysis, 4 free parameters to be taking over. To name these are the gas temperature, the species column density, and the beam filling factor. So from our results across the state, we see consistently that SIO and HNCO are tracing very different gas properties. So in individual corner plots, I place in the bottom here, HNCO are in green and SIO in purplish blue. So it's, you can see across these 3 regions that I show here, HNCO always tend to trace denser gas component compared to SIO. The temperature, which is pitched in the second column in individual corner plots, the HNCO is pointing always towards older gas components compared to SIO. So this provides a very strong evidence that these 2 species are pointing to very different gas components. But chemically, as I already stated earlier, earlier minutes, that both are thought to be shock tracers. So there's coherent properties that, something is coming together. What I'm saying here, sorry. So, and this drive us to further to chemical modeling to see if we really, if we can see somewhat consistent. And yeah, so again, showing this building blocks flow of thinking, then we to perform chemical modeling. So, so these are a few, just one example from our many models in the paper. So basically, in individual subplot, we put the chemical fractional abundances for each species, where we plotted HNCO in blue, SIO in orange, and additionally, we also plot the atomic silicon in green. And in the background, we also provided the gas temperature, which is signaling the proceeding of the shock. So basically, it plots the shock profile. So on the left-hand side column is the modeling performed with shock chemistry. On the right-hand side is just non-shock, basically thermal sublimation. So what we concluded from the modeling we performed here is that SIO, as consistently with previous study, SIO is actually really sensitive to fast shock only. So say shock velocity around 50 kilometers per second, and HNCO is uniquely tracing slow shocks. So, so combining the pictures that these 2 species are tracing very different gas properties, plus they are tracing different shocks. So things starting to get, we are starting to be able to put pieces by pieces together. In essence, from our analysis by far is that for our observed NGO and SIO, we require shocks, but different type of shocks for each species. And when we look back to our gas property profile, gas temperature, gas density, etc., if we are assuming, both species are derived from the post-shock episodes, then what we are actually seeing here, in particular for the, they are actually the post-shock cooling gas temperature in individual gas components. They are potentially at very different cooling phase, basically. So, and for different gas density, for example, the post-shock cooling time would vary. Like for denser components, it takes them shorter time scale to cool down to very cold gas temperature. For very thin or very diffuse gas, it takes much longer. So this actually provides us another sense of time scale in terms of these shock regions across the CM. Easier to imagine or to comprehend. Here is my little thought experiment plot. So, for example, for the GMC7, this is one of the regions that we study. We found that HNCO is tracing gas density around 10 to the 5. So here is the shock scale. This is line where we mark the influence of the shock, across the gas component. So, so in HNCO, in this particular GMC, we measure very cold temperature traced by HNCO. So it means that the time scale since the last shock episode that this gas parcel experiencing has been much longer than the shock influence time, which is I plotted here around 10 years. So thus the green arrow, it's like it must be taking much greater than this 10 years time scale. On the other hand, for SIO, you notice that it's tracing very low gas, but the gas temperature traced by SIO in this region is still hot. It means that this gas parcel is still around is still well within the shock influence. So thus this, blue little dash, it means that it's still around most fiercely influence the gas parcel. So so this gives us two sense of time scale. If we take one step further by assuming that these two species are actually pointing back to the same shock episodes, it's just influencing different parts of the gas. They are influenced by the same shock episodes, and we take intersection of these two timescale and make it this dark pink one. We call it joint shock timescale. But this is actually a very strong assumption. It means thought experiments we played how much we can push this understanding. So in the end, we also plotted the
2 minutes left.
Thank you. So in the end, we also plotted the distribution of joint shock time scale across all the CMZ, and we actually found there seems to be a distribution. So this is quite interesting because we know that in the CMZ of this galaxy is owning a very large scale outflow that's driven by starburst episodes. So this could be associated in a certain way. So in our paper, we also explore in individual CMZ, in individual GMC, that where and how these shocks could come from. It could come from either outflow from the mini starburst episodes. It could come from or it could be sporadic. Like I said, if you want to take the intersection of the two time scale, then you must assume that these two shock episode traced by two species are associated, but in the sporadic shock scenario, it doesn't have to. So yeah, we explore a lot, but I only have this amount of time. The takeaway here is that we found out in this paper that HNCL and SIO are probing different parts of the shock regions, combining our understanding from radix modeling and chemical modeling. And also realize it's actually very important and very much fun to have a collective picture from both sides of modeling analysis. And we also found out that it's possible to infer the age of the shocks from the measured gas properties by individual molecule and individual GMC regions. And we found that if we assume the shock episode traced by these two species are associated, there seemed to be a trend along the distance from the galaxy center that could be associated with some global features in the CMC region of this galaxy. So I'll stop here, and I'm happy to take questions.
Thank you, Monica, for this really nice talk. Do we have questions? You can raise your hands or ask in the chat. Okay, so I will ask a question, and if we have questions in the audience, just please let us know. I have a question, like, what is the amount of silicium you put in your grains in your chemical model? Do you vary that or not?
So in our chemical modeling, we assume so there is initial silicon, right? We assume that like 99% or more is depleted into the grain core. So in terms of gas phase silicon, it's depleted to like 1% level of the solar abundance. But in the strong shock scenario, because the strong shock will destroy like the grain entirely, so the 99% of silicon locked in the core of the grain will be released in strong shock scenario. Otherwise, it's depleted into the core of the grain. So yeah.
Okay, thank you. We have a question from Maria Stone. Is there any similar systems around? Sorry, the question is, are there similar systems around?
Similar system around, meaning similar.
I can explain, like similar galaxies,
Sorry.
With similar processes. Do you observe it in this one?
Yeah, indeed. Do you mean like Starburst system?
Yeah, you can take it however you want, because it's one galaxy you are talking about, right? The NGC253. Is there something so particular about it, or similar galaxies to it in mass, or will have similar phenomena, or is it only this type of galaxies, or other galaxies also have the same?
You mean in terms of the shock properties that we survey here?
Correct.
Yeah. So ALCHEMI, it's special because it provides us tons of molecular lines. So I think this is probably the first study we can go such well characterized properties, but indeed there are last year we have a paper that's studying another galaxy but it's AGN host galaxy, but we were using the same pair of tracers, and they are pointing to similar properties. Like these two species are pointing to different gas properties, gas components, and different shocks potentially. and I think there are more other galaxies that's worth exploring. That will be fun to see if we can survey targets, see if we are able to get a coherent pictures that we see here from ALCHEMI. Yeah, yes, absolutely.
Thank you. And I'm not expert, just was curious, especially the AGN part was interesting. Thank you.
Yeah.
Okay.
No,
thank you.
Thank
you, Maria, for these precisions. I think we will. You will need to take your question to Slack, Sebastian, because we are running a bit out of time. So maybe we can have the next speaker thank again, Monica.
I'll copy the question in Slack channel, so discussion can continue there.
Thanks, Marcella.
Yeah, I'll take over from there. Thank you, guys.
Thank you, Monica.